Good evening. Welcome back to AP Stats Notes Online. We're going to continue talking about random variables, and in particular, tonight talk about what are called binomial random variables. So, we need to recognize binomial settings. For example, if you flip a coin 5 times, and you define a random variable as the number of heads you get, that's a binomial setting. If you consider randomly selecting 100 babies and define a random variable as the number of females in those 100 babies, that is a binomial setting. What a binomial setting is, okay, is a situation where your outcomes are binary, right? And what binary means is two outcomes, bi meaning 2, right? So we're looking for 2 outcomes. And so we'll consider those and we'll call those successes or failures. And it is important to understand that just because we call something a success or a failure doesn't necessarily have the negative or positive connotations that you might think with success and failures. For example, if I'm going to randomly choose 100 babies and consider how many of them are female, then when I select one baby and that baby's male, that doesn't mean, that would be a failure in our binary situation here, but obviously male babies aren't failures in the negative connotation. So anyway, we'll talk about successes and failures. Am I getting what I want to count or am I not? So that's binary. So yes or no type of situation. Each trial in our random process needs to be independent. Okay? The outcome of one trial cannot depend on the first, right? The outcome of one trial cannot depend on the outcome of another, right? Cannot depend on another. So when I flip a coin 5 times, the second flip outcome is not going to depend on the first flip outcome. When I select 100 babies at random, the sex of the second baby is not going to depend on the sex of the first baby. So those are independent trials in this setting. And then if I'm telling you that I'm going to flip a coin 5 times, or if I'm telling you I'm going to select 100 babies randomly, right, then the number of trials needs to be set. And so I'll leave this at number. And so the number of trials is already known. Okay? So 5 flips, 5 trials, 100 babies, 100 trials. The number of trials is already known. And then the last setting is that your probability of success or failure is the same for each trial. Okay? So I'll just say the probability of success is the same for each trial. Okay? And so again, whether we're talking about flipping a coin 5 times and counting the number of heads, or randomly selecting 100 babies and finding out and counting the number of females, all of these conditions are being upheld. So binary, independent, number of trials needs to be set, already known, and the probability of success needs to be the same for each trial. When you're flipping a coin, you've got a 50-50 shot at getting a heads each time. Each time I randomly select a baby, we've got basically a 50% chance that baby is going to be male or female. So we do create an acronym, as we do for everything else, right? SOCS for describing a distribution, DOFS for describing a relationship in a scatter plot. And in a binomial setting, to see if something fits into a binary setting, we're going to check our bins. Okay? Is it binary? Are each trial independent of each other? Are the number of trials set before we get going? And is the probability of success the same for each trial? Okay? So then that leads us to a binomial random variable. Okay? Definition of a binomial random variable is simply a random variable, so it's still going to be a variable that describes some chance process that takes on numerical values, right? So it's a random variable that counts the number of successes in a binomial setting. Okay, so we get a binomial random variable. What are the possible values of a binomial random variable? Well, if you think about it, if I'm going to flip a coin 5 times and count the number of heads, the possible values are 0, 1, 2, 3, 4, 5. If I'm going to randomly select 100 babies and count the number of females, my possible values would be 0, 1, 2, 3, 4, 5, all the way up to 100. So what are the possible values of a binomial random variable? They're going to be whole numbers. They're always going to be whole numbers. And they'll be whole numbers from 0 to however many trials we've got, right? Because we're counting successes. Depending on the number of trials I run, all of them could be successes, or none of them could be successes, and we can have some number in between, okay? So if you're thinking about a binomial distribution, you're always going to start at 0, and then your distribution would carry on all the way out to however many trials you got. So, and they're whole numbers, gaps between. And so a binomial random variable is basically a discrete random variable, okay, as opposed to a continuous. All right? What are the parameters of a binomial distribution? Well, in order for us to create a distribution, right, if x is a binomial random variable, in order for us to create the distribution, remember a distribution with all the possible outcomes of a variable and how often those values will occur, then I have to know the number of trials, because then I know I'm going to start at 0 for my possible values and go all the way out to the number of trials. So we'll denote n as the number of trials. And then the second half of a distribution, of a probability distribution, is the probability of success, right? So P, this is your probability of success. Okay, so we'll always need to, 1, define or tell if a random variable is binomial, because it fits the setting, and then we'll always need to indicate the number of trials and the probability of success. That's going to be part of showing your work in a binomial probability problem or calculation, okay? Now, some other things to keep in mind before we start talking about binomial probabilities. Number 1, what is the most common, the next thing is, next question in your notes, what is the most common mistake students make on binomial distribution questions? Well, quite simply, is that students don't recognize binomial settings, okay? This stuff, this binomial probability stuff only fits for binomial settings. So students very often do not recognize binomial settings. Okay? And so it's important to start getting into the habit of checking those conditions: binary, independent, number of trials, are they set? And is the probability of success the same for all of your trials? Especially if you get to a probability problem that you don't know how to do, right? Or you're not sure how to do. The very first thing I would do is check your binomial conditions. So the moral of this story is, check your bins. Always check for bins in a probability question, right? Especially if you're not sure where to get started in the problem. Now, maybe the bins don't hold up and you got to think about it in a different way, but you need to at least start there, okay? All right. Well, we can't get into calculating binomial probabilities unless we understand and recognize binomial settings. So, in these next couple of 3 ABCs here, let's see if we can't figure out if the situation described is a binomial setting. Okay? So A says, roll a fair die 10 times and let X equal the number of 6s. Okay? So think about that. Is this situation binary? Do we have basically 2 possible outcomes? We're defining our random variable as the number of 6s. So when I roll a die, what am I counting? I'm either counting that there's a 6 or there's not. Okay? So, yes, this is binary. We're counting 6s or not. Okay? Is each trial independent? Well, we're rolling a die. Does the roll of the second die depend on what the outcome of the first die was? No. So we can say rolling a die is independent. Okay? Is the number of trials set before we get going? Before I even do the random process, are the number of trials set? Yep, we're going to do 10. We're going to do 10 rolls. And is the probability of success the same for each trial? Every time I roll a die, is the probability of getting a 6 the same? Yes, it is. So there's a probability of getting a 6, which is 1 in 6 for each trial. So is this a binomial setting? Yes, this is a binomial setting. What about B? Shoot a basketball 20 times from various distances on the court. Let Y equal the number of shots made. Think about it for a second. And then look at C also. Observe the next 100 cars that go by and let C equal color. Think about that for a second. Stop the video if you'd like, and then we'll check what you got. Okay, good. Did you get no for part B and no for part C? I hope you did. Now, why is part B a no? It fits everything up until the probability of success, right? Ben's binary is upheld because you're either going to make or miss the shot. A lot of research does show that each shot is independent of each other. Although, I don't know, being a basketball player, it's hard for me to understand that. But anyway, we'll go with the research. And then the number of trials is set at 20. However, the closer you are to the basket, the more likely you are to hit the shot. So your probability of success breaks down. In part C, your binary, the very first thing you check, binary isn't upheld because there are more than 2 outcomes. If we're just going to look at the color or even count the colors, there's more than 2 outcomes. So it's not binary, so no. So be able to recognize the binomial setting. In part A, we could go ahead and start trying to calculate binomial probabilities. Okay? All right, speaking of which, let's start talking about that. In many games involving dice, rolling doubles is desired. Rolling doubles mean the outcomes of 2 dice are the same, such as 1 and 1 or 5 and 5. So hopefully you guys understand that, right? If you're playing Monopoly, rolling doubles is good because you get to go again. The probability of rolling doubles when rolling 2 dice is 6 and 36. You can get a 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6, right? There's 6 different outcomes out of 36 possible that gives you doubles, so 1 and 6. If we define a random variable x as the number of doubles in 4 rolls of 2 dice, then x is binomial, right? Binary. It's either going to be a double or it's not. Each roll is going to be independent of each other. We have a set number of trials already, which is 4, and the probability of success is going to be 1/6 every time you roll the 2 dice. Then the number of trials is 4, the probability of success is 1/6. That's what we need, okay? So what is the probability that x equals 0? We've done this before, right? If I want to know the probability of x equaling 0, well, then I've got to find all the different ways that can happen and what the probability of each roll is, right? So in other words, if I get 0 doubles, right, what's the probability that all 4 rolls are not doubles? Well, think about it. That means in terms of success and failure, either doubles or not. Then that means the first roll has to be a failure, right? The second roll has to be a failure, third one has to be a failure, and the fourth one has to be a failure. Is there any other way that happens? No. So what's the probability of not getting a doubles the first time? Well, if you have a 1 in 6 chance of getting doubles, that means you have a 5 in 6 chance of not. Right? And we've gone through this kind of stuff before. So the probability of not getting any doubles is just going to be 5 out of 6 multiplied by itself 4 times or raised to the 4th power. And there's exactly one way that's going to happen. So I would take 1 times that 5, 6 to the 4th. Now, it's unnecessary, but there's a reason why I'm putting it in there, and I'll show you why in just a second. Okay? All right, so no problem. We can go do 5, 6 to the 4th power and find that probability. I'll let you guys do that. We'll move on. What's the probability that we get exactly one set of doubles? Well, let's think about what that would look like as far as our 4 rolls. I could get a doubles as a success and then have 3 failures, or I can get the success on the second roll, or I can get the success on the third roll, or I get the success on the 4th roll. Okay? So there are 4 different ways this is going to happen. Is the probability going to be different for any of these 4? Well, how would you find it here? There's a 1 in 6 chance of getting a double, so my first roll is a 1 in 6 chance of me getting a success. And then my next 3 would have to be failures, and the failure rate is 5 in 6. So it would be 5, 6 to the 3rd power. It's the same here. Doesn't matter if I get the success on the 2nd, the 3rd, or the 4th roll. All of these are going to be 1/6 to the 1/6 times 5, 6 to the 3rd power for all 4 of these. So I would take this, or this. So I got to take all of these. I got to take this same probability calculation and add it to itself 4 times. Or another way to do that is just multiply this whole thing times 4. Okay? I want to go through this kind of quickly, so if you're not quite picking this up, make sure you come talk to me and I'll tell you where all these numbers are coming from. But we've kind of done this before, so I want to do this kind of quickly. So again, you can go multiply all that out and find that probability. Again, I don't want to take that time or insult your intelligence. I'm sure you could go do that in your calculator. Okay? Well, let's keep going. So we've got 1, and I want to kind of put these together so we can see them. Okay, so I'll get to write these down pretty quickly. 1 times 5, 6 to the 4th. This became 4 times 1/6 times 5, 6 to the 3rd. Now, what about x's if we want exactly 2 doubles or 3 doubles or 4 doubles, right? Let's do these pretty quickly and see if we can't find a pattern. So 2 doubles. That can happen if I get a double, double, not double, or go through all of your different possible combinations. Okay, there's 1, 2, 3, 4, 5. I feel like I'm missing one. I could get, let's see. Oh, I somehow missed 2 in the middle. So I can go this, this, and this. Okay, so there's 1, 2, 3, 4, 5, 6 different ways this can happen. So I'm going to take the same probability I get for 1, since the 6 are not going to change. So I can take the probability of one possible outcome, which is going to be success times success, or 1/6 to the 2nd power, 1/6 squared, times failure, which is 5/6 squared. And there's 6 different ways I do that. So I can take 6 times 1/6 squared times 5/6 squared. And have you seen a pattern yet? Look at your power on 5/6, and then look at your power on 1/6. Right? There should be a bit of a pattern developing here. And then you don't know the pattern yet to this coefficient out front, but we'll talk about that in a second. Right? So that's all the different ways I can get 2 doubles. How about if I get 3 doubles? Well, I can get double, 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 not double, double, not double, double, not double, double, or not double, double, double. 4 possible outcomes. What's the probability of each? Well, now I've got 3 successes, so it's going to be 1/6 to the 3rd power times your failure, which is 5/6. And there's 1, 2, 3, 4 ways that's going to happen. So I'll take 4 times 1/6 to the 3rd times 5/6 to the 1st, really, right? I didn't do that to the 1/6 up here, but and again, there's a reason why I'm putting it in. You don't need it. There's a reason why I'm putting it in. Now, how about getting 4 doubles? There's only one way that happens. Success, 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 and the probability is just 1/6 to the 4th power. There's only one way that happens, and the probability is 1/6 to the 4th power. Now, what happened to the 5/6? It went away. 5/6 to the 4th, 5/6 to the 3rd, 5/6 squared, 5/6 to the 1st. So then this is basically 5/6 to the 0 power. Anything in the 0 power is 1, and so we don't really need it. And kind of the same thing up here. If you go backwards, 1/6 to the 4th, 1/6 to the 3rd, 1/6 squared, 1/6 to the 1st. That means that really we needed a 1/6 to the 0 power up here. But again, we don't need it because 1/6 to the 0 power is just 1. But that helps us establish a pattern, okay? And that's what the next question asks. How can we calculate a binomial probability in general, okay? Well, if you look, when we wanted 0 successes, my success rate was raised to the 0 power. When I wanted 1 success, my success rate was raised to the 1st power. When I wanted 2 successes, my success rate was raised to the 2nd power, and so on and so forth. Okay? Now, your failure rate went opposite, right? Out of 4 trials, 0 successes, I raised my failure rate to the 4th power, and I reduced 1 every time. So there is a pattern here, and that pattern is basically this. If I want to find the probability of, call it K successes, okay, I want to do this in the general sense, right? Then what that means is apparently I'm going to take my success rate, which is P, and raise it to the K power, okay? I already know I've got N trials, okay? So look at what happened. Every time I got a K, I had to take my N, which up here N was 4, and subtract the K from it to get my failure rate power. So it means I'm going to take my 1 minus success rate and raise it to the N minus K power. Now check that out. Up here, again, my number of trials were 4. So every time you come up here to a failure rate, look, 5/6 to the 3rd. Well, that's just my number of trials minus the number of successes I wanted, N minus K. This is N minus K. This was N minus K. K is 2, N is 4, 4 minus 2 is 2. And so I keep sort of that same pattern for my failure rate and success rate. Now, the big question is, where is this combination, where is this possible number of combinations of outcomes coming from? And the last thing we want to have to do is come up with a sample space every time we want to do a probability calculation. For example, if I'm going to randomly select 100 babies, the last thing I want to do is come up with a sample space of 50 of those babies being female. There's a lot of different ways that's going to happen, right? Well, we use what's called the binomial coefficient, and I'll write it up here. The binomial coefficient gives us our number of possible outcomes. Okay, this tells us our number of possible outcomes for whatever situation we want. Whatever we're counting, right? And that's calculated by this, right? We denote it in a couple of different ways, right? We do it like this, and we read this as N choose K, right? I've got N number of trials, and I'm choosing this many successes, okay? It's also written as this. Since we read it as N choose K, then think about it as N choose K K this way. You'll also see it denoted this way. The C just stays a C, stands for choose. Actually, C stands for combinations. This is the number of combinations we can get, but for us, we can read it as choose, and it's still fine, okay? Now, how is it calculated? It's calculated like this, and I don't know how much time we need to actually spend on doing this, okay? But it's n factorial divided by k factorial times n minus k factorial. I'll show you how that works once, and then I'm going to show you in your calculator how to get that, and then we're going to be done with it, okay? You have to remember what factorial means, okay? And factorial means, if I do n factorial, that basically means I take n times 1 less n times 2 less n times, and keep going until I get down to 2 times 1 times, well, not 0, 2 times 1, right? I'm basically factoring down, no, that's not true either. I'm basically reducing it by 1, whatever n is every time, and multiplying all those numbers together. Okay, and it's kind of weird without an example, and I'll show you what that looks like in just a second. But that's where the number of combinations come from. I knew there were 6 combinations here, right? Because I did 4 choose 2. And I'll show you how that works on the next page. Okay? Don't worry a whole lot about it. We're going to use our calculator to do a lot of this stuff. All right? All right, let's do that then. Let's go take a look at the next page and start trying to calculate these probabilities. Okay? All right. In roulette, 18 of the 38 spaces on a wheel are black. Suppose you observe the next 10 spins of a roulette wheel. What's the probability that exactly half of the spins land on black? Well, you want to check your bins, binary. 2 possible outcomes. Either it's going to land on black or it's not, right? Independent. Each spin of the wheel should be independent of each other. Are the number of trials set? Yes, there's 10. Is the probability of success the same each time? Yep, it's going to be 18 out of 38 each time we do it, okay? So, what's the probability that exactly half of the spins land on black? Well, that means the probability that x equals 5, right? So x is a binomial random variable where n is 10, n is the number of trials, and the success rate is 18 out of 38. And you need to outline that every time you do a binomial probability problem, okay? So how do we do this? Well, if we go back to the formula, and we didn't actually finish writing this in, we ought to do that. So if you go back, I'm sorry, real quick to this page, we need to put in our binomial coefficient right here, right? And that was just your n choose k, okay? That's how we got those coefficients, 1, 4, 6, 4, 1. Okay, so it's going to be n choose k. Let's go put this to practice. Okay, what does that mean? Well, my n here is 10, my k is 5. So now I want the possible combinations of 10 choose 5. And then I'm going to raise the success rate to the k power. So my success rate is 18 out of 38. I'm going to raise it to the 5th power. And I'm going to raise my failure rate, which is going to be 20 out of 38. Right, I get that by doing the complement of 18 out of 38, subtract that from 1. And I'm going to raise that to the n minus k power, 10 minus 5, which is just 5. Okay? Now, n choose k, what is this number? Right? And again, we can always write it as this. And you'll see it written like this. You need to understand both notations. What that means is 10 factorial over 5 factorial times 5 factorial. And you can go back on the other page and verify this is n factorial over k factorial times n minus k factorial. So let's write it out real quick. Only time we ever do this. Not 10, so that means 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1 times 5 times 4 times 3 times 2 times 1. That's what we meant. That's what I meant by reducing n each time and multiplying all those numbers together. Now, watch what happens. Since we're dividing, a lot of factors start canceling out, or dividing out. I shouldn't say canceling out, right? So This 2 and this 2 divide out, this 3 and this 3 divide out, this 4 and this 4 divide out, this 5 and this 5 divide out. I can take this 2 and this 3 and divide out to 6, right? Because 3 times 2 is 6, so these guys divide out. My 4 divides into the 8 twice, and my 5 divides into the 10 twice. So everything on the denominator is gone now. But in the numerator, I'm left with 2 times 9 is 18, times 2 is 36, 36 times 7. Let's do that quick math. It's 2, this is 4, this is 252. So there's 252 different ways that we can get 5 blacks. So 252 times 18 over 38 to the 5th power times 20 over 38 to the 5th power. And that should get you, and I'll tell you, you can always verify that by plugging it in. And that value is something I don't have on me right now. Well, whatever that is. I'll show it to you tomorrow. Okay? So that's basically what this means. Now, I'm not going to do this anymore. Okay? For now, that's how we're going to go about doing these binomial probabilities. Okay? Now, to save some time, we need to also talk about how to find the probability that x is at least 8. At least 8 means greater than or equal to 8. Okay? But how about we talk about that in class very quickly tomorrow, as well as take any of your questions and do some homework there. Okay? Let you think about it. You can give it a shot if you want to try and think your way through that. And then I'll also show you how to use your calculator in terms of doing these probabilities also. Okay? But that's where it comes from. And we'll finish this up tomorrow in class. Have a good night. See you tomorrow.